Hi, well, we're lucky to get Andrea Young today to give our seminar. He was really one of the founders of the whole field of graphene. He got his PhD working with Philip Kim at Columbia back in the days when the first things were happening. He went on to do a Pappalardo Fellowship at MIT, and then went to the Weizmann Institute as a visitor for a year, and then to his current home at the UC Santa Barbara. He's won a number of prizes, including the Macmillan Prize in 2016 and a Packard Fellowship, along with a Sloan Research Fellowship in 2017, as well as some other awards. He's going to talk about today about sort of twisted magic angle graphene, which we've seen before, has remarkable properties because the little eyes of the Moires create a low density electron gas that has unusually high degree of correlation, including superconductivity and insulator states. A new thing is everybody knew about ferromagnetic carbon, right? So today he's going to tell you how this new system actually makes a ferromagnet beads like a topological insulator in some ways. So I look forward to hearing this. Andrea, thanks.
Sure, thanks, and thanks everybody. It's a pleasure to see so many familiar names in a little box. Not as pleasurable as maybe seeing the faces. So I'm gonna ask a favor of the audience, which is just to please interrupt as I go along. I'm at this point probably as expert as any of you at fielding questions in the chat box while I give a talk or teach. So please, as things go, interrupt me. It'll make me feel less like I'm just spending the umpteenth hour screaming at my computer screen by myself in my garage, which like I'm sure for many of you has been my existence for the last innumerable months. So, okay, so anyway, so please interrupt. I've got the Q&A and the chat open, and I look forward to hopefully enough discussion that, that it'll almost remind me of visiting. So, so I'm gonna tell you about a kind of string of work that we've been doing in my lab over the last couple of years, focused on trying to understand and control orbital magnetism in graphene heterostructures. So let me give a sort of extremely broad kind of intro to why I think this is interesting. So ferromagnetism is an ancient phenomenon. It was apparently first reported by Thales of Miletus in the 5th and 6th century before the Common Era, who just noted the attraction of magnetite to iron. And his conclusion was that matter is actually alive. And so this turns out to not be true. And theories of magnetism have improved a great deal since then. In particular, an important result that motivates a lot of our study of magnetism is that there is no classical magnetism. So magnetism of any form, this was actually Bohr's PhD thesis, is that the free energy is independent of the vector potential classically, and as a result, there can be no magnetic moment and therefore no magnetism classically. But from another point of view, most magnets that have been studied since the time of Thales have been of the same fundamental type in that they basically involve a conspiracy of electron-electron interactions and Fermi statistics, which generate a ground state with a finite spin polarization. And so the basic physics of this is very simple. You have repulsive Coulomb interactions and Fermi statistics. So if you imagine, for example, a pair of finite square wells, and you consider two electrons, within them, they have a in the absence, of any coupling between the wells, they have some degeneracy between symmetric and antisymmetric orbital combinations of these two wave functions. But then that gets split by the Coulomb repulsion. And if that splitting favors an antisymmetric wave function, which in this particular example, which you can find in Landau and Lifshitz, it does, then that means that in order to maintain antisymmetry for the whole the whole electron wave function, including the spin, you need to have a symmetric spin wave function that favors a finite angular momentum ground state. And now you can think about, of course, a model that for macroscopic collection of spins that was generally attributed to Heisenberg. And in 3D, you'll get some ordered state below some critical temperature, which can be the ground state will just simply have all the spins aligned in the same direction. In 2D, of course, a little bit more complicated. To get true long range order, you need some amount of anisotropy. So you need kind of to restrict those spins to point either up or down. Most of the time in condensed matter systems, that anisotropy that favors an easy axis for the spins comes from spin orbit coupling and crystal field splitting and so on, which will tell the spins a direction that they should point preferably within this type of model. And that's basically how most ferromagnets work. So another point of view that is related is that in order to make a magnetic state, you need to make in a solid, you have bands, right? You don't just have perfectly localized electrons. The electrons can move around. And so the electrons have kinetic energy, and there's a trade-off between making a magnetic state, which will cost kinetic energy because you can only singly occupy these single particle states, and exchange, which would favor that single occupation. And so this is captured in a very simple picture by something called the Stoner criterion, which basically says that when your exchange is strong enough, in particular, when your exchange is strong compared to the bandwidth or really strong compared to the inverse density of states, then ferromagnetic states will be favored, and disordered states will not be favored. And in the other limit, it'll be the other way around. So this gives you a basic sort of more of a rule of thumb. This doesn't have much in the way of microscopics for when you expect ferromagnetism, and really when you expect correlation physics in general. It's when the density of states is very high and the bandwidth is narrow. So the talk today is going to be about graphene, which is of course a very unlikely magnet based on the considerations that I just laid out. So it's certainly very two-dimensional, so that's already kind of bad for long range order. The orbitals in graphene are very delocalized, so you don't expect a very large density of states, and there's no spin orbit coupling to speak of. So that's a mechanism that's sort of out the window. So the talk I'm going to give today is really about a different route towards ferromagnetism, which is really based on orbital degrees of freedom. And those orbital degrees of freedom in the case of graphene come from the valley degeneracy. So I think for this audience, based on a quick perusal of the chat, I don't think I need to explain very much of this, but for the record, in graphene, due to the symmetry of this lattice, the low energy electrons are concentrated around two inequivalent valleys, which in monolayer graphene with no additional perturbations of any kind are perfectly degenerate, and they basically constitute a microscopic degree of freedom, which is related to the relative phase of the electron wave functions on the two carbon sublattices, but behaves effectively as an internal degree of freedom. But what I'll show you is that this internal degree of freedom can behave rather anisotropically. So in other words, it can, these are indeed ultimately correspond to real space, magnetism of valleys corresponds to real space orbits in the 2D plane. They're very anisotropic. That gives you an Ising-like degree of freedom. And more or less the story of this talk will be that you can get magnetism from that, and that is a different type of magnetism than with spins. In particular, it ends up allowing you to have rather more control over magnetic ground states, especially using electric field-based knobs than what you can easily get in a spin-based system. So the basic physics of how that works comes from this idea of, one can ask the question, and surprisingly, this was really only worked out in the 90s and early 2000s of, what is the for a crystal where the wave functions are described by Bloch states, what is the orbital magnetization? And it turns out that this is something that you can solve, and it relies on two things. There's the wave packet self-rotation contribution and the center of mass motion of those wave packets, which depends on the Berry curvature. But the basic point is that there's an orbital magnetization that is associated with quantities that are derived from the details of the Bloch functions. And usually this is not a big effect in magnets because most of the time you have a very large density of spins. There are some exceptions. So there's this samarium gadolinium aluminum compound where they found that it's a ferromagnet and that they see magnetic hysteresis and so on, but the actual measured total magnetic moment was found to be essentially unmeasurably small. And this was attributed to having a sufficiently large orbital magnetization that it canceled the spin contribution to the magnetization. Maybe the physical picture that's going to be relevant for us today is comes from this sort of seminal work about graphene, where it was pointed out that if you have a Dirac point and you gap it out, let's say you gap it out by just introducing a mass, we'll do it by having either an electric field in a multilayer or a boron nitride substrate on twisted bilayer graphene or monolayer graphene or so on. You will generate some gap, and that gap generates a finite M. If you just look at the block functions expanded around the K point, you'll find that in fact there's you generate finite M and finite omega. That comes, however, from these block wave functions. It is by necessity canceling in two different valleys because, of course, you're not going to have any. If you demand time reversal symmetry, you won't have any magnetic moment. And so the second ingredient that we need is the Stoner criterion to be fulfilled. And in essence, we need to increase the density of states and generate the tendency towards actual spin and really particularly valley ordering. So this is not a historical talk. In fact, I'm going to spend the first, in the hope of showing you something that you can't read online. I'm going to spend the most of the talk talking about some new and unpublished data in a very simple system, specifically rhombohedral graphite and rhombohedral trilayer graphene with no moire, and show you how, in fact, all the ingredients and indeed many of the phenomenologies of interacting physics that we've come to associate with twisted heterostructures are actually, you don't need to twist anything at all. And the basic physics of twisted heterostructures is fundamentally actually that of itinerant magnetism. And it's present, for example, in most graphite, I think, and certainly in ABC graphene. And then I'll try to spend the rest of the talk telling you about what it is you actually gain by having a moire pattern that is different from the perfectly lattice-free case. Okay, so monolayer graphene, so why graphene multilayers in the first place? Well, in monolayer graphene, you have this very unfavorable situation where you have gapless Dirac points, very extended delocalized wave functions, and a rather small density of states. In bilayer graphene, things get a little bit better. Your density of states gets to be approximately, again, this is in the simplest two-band approximation. You have now replaced your Dirac cones with touching parabolas, so they have a higher density of states, but still not terribly high. But the situation that I want to focus on is what happens when you apply an electric field across, for example, a bilayer. Then, because you had these touching quadratic points, touching quadratic dispersions in 2D, when you gap them, you get effectively quartic dispersions. And that gives you 1D like Van Hove singularity, a 1 over square root n Van Hove singularity in these systems. And that is naively a very favorable situation for magnetism and strong interaction physics, because you have a very high density of states at the band edges in bilayer graphene. And indeed, I think this was immediately figured out. So there was the earliest paper that I could find that focuses on this specific situation was very shortly after the discovery of graphene, and bilayer graphene was pointed out that this should be a ferromagnet at low densities. It's of course not so different from what happens and what's been thought to happen since the days of earlier predicted in theory, for example, from quantum Monte Carlo, of just low density two-dimensional electron gases should have magnetic regimes. Here, you're helped out by the fact that actually the RS parameter becomes very large when you have such a large density of states. And so you expect this to be a very robust type of physics. So how do we do this? Let's say we want to explore this regime explicitly. Well, it's the standard things that we do in this field at this point. The key things are you need to be able to realize okay, bilayer graphene, I'll show you actually turns out you need trilayer graphene for reasons that are maybe still a little mysterious. And you need to keep things very clean because any disorder will broaden this Van Hoff singularity, decrease the density of states, decrease the importance of interaction effects. So, okay, I think, you know, everybody here knows the basic picture. I'm stealing slides. This animation I stole from my first student, Sasha Zebrov's PhD thesis, who I think is in the audience. And I think he made this video, so credit where it's due. But we do this in the way that was developed, you know, over a variety of years and groups, particularly in the group of Corey and Philip back at Columbia, where you can build these very complex van der Waals heterostructures using this pickup method by picking them up with polymers one after the other. I think the key thing that we're rather religious about in my group is trying to do this at the frontier of the highest possible electronic quality. And that for us has meant, here's an example of the type of stack that we may make, but using graphite gates for everything and making sure that that you don't have either amorphous dielectrics, but also having no amorphous metals or any surfaces that have any contamination that are electrically visible to the 2D layer of interest. Right, so, you know, this has been successful in the sense that, you know, we can now make reliably very clean two-dimensional electron systems. So for example, if you look at Landau level broadening in clean monolayer graphene made in this way, you find that it's on the order of 5 to 10 Kelvin. And that's a bit worse than the highest mobility gallium arsenide, which is sort of in the range of 2 Kelvin, but not dramatically worse. And the measurements that I'm going to show you for the first part of the talk are measurements of the penetration field capacitance. So here's an example, and basically that is measuring the inverse compressibility. So you can look at this color scale, and high means high inverse compressibility and low means low inverse compressibility. So so here, for example, you see these are integer and fractional quantum Hall gaps measured in bilayer graphene and high magnetic fields. And you can see sort of a wealth of correlated states. And then you can look at bilayer graphene. So at zero magnetic field, so precisely the range where ferromagnetism is expected. And an interesting thing, you know, which we just sort of filed away to, well, okay, maybe the theorist had something wrong, is that if you look at bilayer graphene, you don't see anything particularly that deviates from what you expect from the single particle picture. So here we're plotting the capacitance. So, so again, this is inverse compressibility. So a peak, for example, in this yellow curve, which is taken at high displacement field, is where the gap at charge neutrality is. And then you see these sharp dips, which are precisely these Van Hoff singularities that are predicted from single particle band structure. And more or less everything we've looked at zero magnetic field in bilayer graphene seems to indicate that single particle physics, perhaps with some parameter renormalizations, is enough to describe it. We have yet to see anything that is dramatically deviates from that. So, okay, so perhaps this is a problem of the basic idea is wrong, but I mean, Stoner physics is rather straightforward. It's something that kind of must happen. It's not a very complicated idea, and it's pretty generically true. So one hypothesis, which we'll explore, is that this is really a matter of degree and not of kind, that the problem here is not that the density of states is not, that the Stoner, you know, the basic Stoner mechanism that was proposed, that this should be a low density ferromagnet, is not true, but rather that for whatever reason, the density of states in that are not quite high enough, interactions are not quite strong enough. Nobody ever really knows what the interaction strength is. So perhaps it's just a matter of degree. And so one idea is to look at more extreme versions of this. And actually the idea that I'll explore first is to look at rhombohedral trilayers rather than Bernal bilayers. This is anticipated by work both from Jeannie Lau's group on suspended layers and by the Geim group on rhombohedral multilayers, where they started to find various signatures of magnetism or metamagnetic transitions at high magnetic fields, certainly things that look beyond single particle. As I'll show you, we can now look at this rather systematically. But let me first motivate just quickly why this is a good idea. So yes, Philip asked, trigonal warping and higher order neighbor hopping in bilayer may screw the simple Van Hoff singularity idea. To some degree, on the other hand, one can look at the experimental data, and this is actually corresponds to a pretty high density of states. So it could be, the thing is that I'll show you, and the real reason why I think the basic idea is sound is that in ABC trilayer graphene, higher order hoppings and trigonal warping are even worse than in bilayer graphene. But as I'll show you, it's definitely all kinds of magnet. So so I still don't know why in Bernal bilayer this doesn't just work. It should have worked. It should have worked 10 years ago. But in trilayer it worked right away. And as I'll show you, the band structure is not that simple sometimes. But even where it's not simple, you get lots of magnetic states. The basic intuition is that ABC trilayer graphene in a simplest model is just kind of uber Bernal bilayer. You can take the same 2x2 two-band model and think about what it is in ABC trilayer, and in the same way that that you end up with really two relevant sublattices on the outer layer in Bernal and dimerization on the high energy sublattices. You'll get that for you'll get two low energy sublattices on the outer layer of ABC trilayer and four dimerized sublattices on the interior. And what that translates to is that now instead of having touching quadratic bands, you have touching cubic bands, which means that now when you gap it with an electric field, you get a sextic band minimum and an even higher order Van Hove singularity. And basically everything is just that much higher, that much more divergent over a somewhat larger density range. And apparently that is enough because as I'll show you, indeed, turns out to be magnetic. It's not so easy to make these samples. I will, a caveat. The basic problem is that unlike Bernal bilayer, which is a ground state of, or at least pretty close to, there's not very many competing states. You can sometimes get domain walls, but for the most part, it is the ground state. ABC is not the ground state of trilayer graphene. It wants to relax to ABA. And so there are a variety of fabrication tricks, which took us some time to develop, mostly having to do with figuring out how to do failure analysis at earlier and earlier stage of the process. But just to give an idea, we use AFM nanolithography to isolate regions of pure ABC graphene, which we identified by Raman spectroscopy. And then we design our stack making process in such a way that we avoid manipulating the ABC more than we absolutely have to, while still maintaining the ability to make dual graphite gates and not have any contaminated interfaces and so on. And so that has worked out. So let me show you the data. So this is the data from an ABC trilayer graphene. There's no Moire pattern. This is just as fabricated. And what I'm showing you again is capacitance. I'm actually plotting it after we calibrate various geometric capacitances. I'm plotting the inverse compressibility on a color scale, right? And so, so let's sort of walk through the basics of this data. So you can see that there are a lot of features here that are tuned by the displacement field and by the density. And in particular, I want to draw your attention to the features in blue. So the way this color scale is structured, black means zero inverse compressibility. So anything blue is strongly negative. And so let me draw your attention first to the electron side. So positive gate voltages. So this is electron doping. And you can see that there's strong negative compressibility at low densities and high displacement fields. And then there are very sharp negative compressibility features that occur at some finite density here, and then another finite density there. Okay, and those are the things I want to first draw your attention to. So here you can see a line cut at zero displacement field and then at high displacement field. The thing that I want to point out is that we can do a very elaborate band structure model of trilayer graphene, and the only feature that you expect to see is actually this feature here, where there's a step in the density of states, and that basically corresponds to Lifshitz transition that comes from trigonal warping and electron hole asymmetry. And this you expect from single particle physics, but essentially you expect a very smooth and unremarkable phase diagram otherwise without electron-electron interactions, because the band structure is actually not that complicated, right? There's really only sort of one interesting thing that happens except at exceptionally low densities. So clearly something is different. And of course, negative compressibility is beyond single particle physics already. So, so what's going on? So, and you can compare this to Bernal bilayer graphene, right? Where over This is over a smaller density range, but there's no comparable features. There might be something broad, but there's nothing nothing dramatic like this at all. You just see the single particle gap, and that's it. Okay, so then we can try to look and see what are these, and actually the answer comes immediately as soon as you turn on a magnetic field. It becomes particularly obvious because you can look at quantum oscillations, let's say at densities and displacement fields corresponding to being inside this region, or this region, and you can find that down to the lowest fields that you can probe, they just have different degeneracies. So quantum oscillations in this lowest density region here, for example, always have one-fold degeneracy. Quantum oscillations in this yellow region always have two-fold degeneracy, and the four-fold degeneracy, which is what you expect from spins and valleys, occurs only in this high density region. And the same thing is true over here. If you take yellow, white, and a blue star that's measured actually off the scale of this color plot, you'll again find the same pattern. There are regions where the quantum oscillations are simply one-fold degenerate all the time, or two-fold degenerate all the time down to the lowest fields. And since these samples are very clean, those low fields are rather low, half a Tesla, you can start to see these quantum oscillations, and there's never any sign of a change in degeneracy. Okay, so it seems relatively straightforward to ascribe what's going on here. Basically, you have a series of first order phase transitions between states that have different spin and valley degeneracy at zero magnetic field. These are all basically just ferromagnets. So here you have, you can, let's again think about the electron side. You start doping, it's a semiconductor. It's a semiconductor that has an unusually high density of states right at the band edge, this big divergence. And when you start doping it, what you do is you make all the electrons go into a single spin and valley flavor. And then at some critical density, it now becomes favorable to take them all out of that spin and valley flavor and evenly split them between two spin and valley flavors. And you can do that for a while up to reasonably high densities of, a significant fraction of 10 to the 12 electrons per square centimeter. And then there's another transition when they transition into evenly occupying all four of these spin and valley flavors. The whole side is more complicated. I'll get to that in a few minutes, but there are at least regions where that's true. There are also regions in between which seem to do something much more complicated. Okay, so we can try to analyze this. So to give you an idea of what the band structure actually looks like, this is a more elaborate band structure model that takes into account basically all of the nearest neighbor hoppings up to gamma 6 and several of the on-site potential differences with sort of the best parameters that we could justify from the literature and from fitting single particle aspects of the experiment that we think are mostly sensitive to single particle physics. And you can see that there's a lot of electron hole asymmetry, right? That's important. And in particular for positive energy, so this corresponds to electron doping, you have this very sharp band edge singularity and a relatively simple band minimum. And for holes, you have something more complicated due to trigonal warping and other terms. So to analyze what happens with interactions, the simplest thing we can do is to make a Stoner model. And the Stoner model basically just says you gain some energy by having your electrons occupy the same flavor. And then you can take this band structure and run that through this minimization of this potential and see what the phase diagram is that you get. And so here's a comparison between our experiment and inverse compressibility calculated by that way. And so you can see that there's a basic match in that the physics of the displacement field dependence of these transitions. So here there are a series of phase transitions between states of 1, 2, 3, and 4-fold degeneracy. And they follow the basic trajectory that we see in experiment, which is basically telling you that this trajectory is linked to density states at the single particle level, just as Stoner would essentially predict. However, there's some pretty significant discrepancies, right? In particular, in experiment, we see a 1-fold state, a 2-fold state, and a 4-fold state. We see no 3-fold state. But 3-fold states, interestingly, seem to be very generic in these calculations. So we've also done Hartree-Fock calculations, but as long as you're using spin and valley symmetric long-range interactions, it seems like getting these states, which would have 3 degenerate Fermi surfaces, happens in calculations, does not seem to happen in experiments. So something else is going on. You can sort of patch that up by doing some violence to this Stoner model if you want, by basically adding very strong valley anisotropic interactions. At this point, we don't have a very good motivation for why they should be so strong. Essentially, maybe a comment for the experts. It seems like you need valley anisotropic interactions that are essentially of the same scale as the long range Coulomb interactions in order to suppress this threefold phase. We don't really understand why that would be. So it's sort of a work in progress, but I'll just make that comment as an aside. One thing we can do experimentally, though, is answer a more basic question, which is, okay, if this is spin and valley polarized and this is filling 2 out of 4 flavors and this is filling 4 out of 4, well, which flavors are actually being filled? There are a variety of possibilities. So one way we can address that that's rather simple is we have these very sharp experimental signatures. We can look at their dependence on, for example, the in-plane magnetic field. So here we can see that the phase transition boundary between a one-fold and two-fold state is not affected by the in-plane magnetic field. So the in-plane magnetic field can couple in a couple of ways, but the most naive one and simplest one is that it simply favors a spin polarized state over a spin unpolarized state. So the fact that this phase transition doesn't move between one-fold and two-fold suggests that they are both spin polarized. In contrast, the phase transition between a two-fold state and four-fold state has a cusp at 0 magnetic field. That implies that there's actually a finite difference in the magnetic moment that couples to an in-plane field between the two-fold and four-fold state, where that moment is larger in the two-fold state, so it lowers its energy more with in-plane field. That's perfectly consistent with both of these states are fully spin polarized, right? The four-fold state is, of course, not spin polarized, and as a result, basically by Pauli exclusion, the two-fold state must be valley unpolarized. Okay, as an additional sort of evidence of this, you can look at just the transport as a function of in-plane magnetic field, and you see that in the four-fold state, there's effectively no dependence on in-plane magnetic field, but there are sharp dependencies on in-plane magnetic field in both the one-fold and two-fold state, indicating that spin is indeed coupled. Perhaps this is coming from scattering off of spin polarized domain walls. We're not entirely sure, but there's dependence also in the transport coefficients inside the bulk of these phases, not near the phase transitions. Okay, let me turn to hole filling. And so hole filling is very complicated. And I'm not going to try to explain to you everything that's going on because I don't actually know everything that's going on. You'll recall, if I can go back a couple of slides, that the hole band is much more complicated. There's in particular there at the densities in question, there are pockets and a variety of Lifshitz transitions at the single particle level. And the Van Hove singularity actually, it's hard to tell here because this is plotted as a function of energy, but the Van Hove singularity occurs at rather a large density, meaning it's not right at the band edge. It's happening a good amount of the way into the, at finite doping. And so you can look at, this is a plot at 1 Tesla in the middle center. And you can see that there are indeed regions where you have very well-defined singly degenerate quantum oscillations, as I told you. Here they're two-fold degenerate, here they're four-fold degenerate, but in between you have these regions of dense Landau level crossings. This is basically associated with having multiple Fermi surfaces when you have, for example, an inner, not simply connected region of momentum space where the electronic states are occupied. A variety of transport phenomenology we're still trying to understand, so measured at various points in this phase diagram. Unusual temperature dependencies, some large anomalous Hall effects, which are interestingly more or less absent on the electron side, magnetic hysteresis, things that you might expect. Other interesting things are that within this one-fold region, we find that the transport at very low temperatures is extremely noisy and extremely sensitive to electromagnetic filtering. So you can suppress this very strongly by going even to a couple hundred millikelvin and by simply not filtering your wires. So again, we think that's associated with domain wall motion in, of walls that are maybe scattering electrons but are very weakly pinned by anything, presumably because these systems are very clean. There's nothing natural for them to couple to. It reminds me a little bit of vortex physics in very clean two-dimensional semiconductors, for example, where there's a very strong dependence on the electromagnetic environment. Let me show you one interesting thing here before I move on to the effects of Moire patterns, which is that for reasons we still don't understand, I think there are new types of phases and phase transitions you can actuate and study here. Before I tell you about the details here, which are a little bit involved, I think let me comment on what I think is interesting about these systems, right? And this system in particular is that, I have spent a long time, and as has Philip and others in this community, trying to understand, quantum Hall ferromagnetism in graphene, which was relatively complicated because you can have polarization into various flavors of spins and valleys. One of the things that always, quantum Hall ferromagnetism always ends in the same way, which is that you end up realizing that as you make your systems cleaner and cleaner, there are some small energy scales coming from either electron interactions, but more often from single particle energies that eventually sort of are the control knobs and reduce the apparent degeneracy to something much smaller than what you thought. So, you think about graphene in some naive way, and you have an SU4 symmetry at high magnetic fields of the spin and valley isospin, but you don't really. There is a lattice, but more importantly, there's also a Zeeman effect when you're doing quantum Hall ferromagnetism. Here, in these zero field structures, you have a little bit less of everything. There's more degeneracy, and the degeneracy is lifted really only by interactions when you're at zero magnetic field. And so that, I think, allows lots more different types of states to occur than are naively going to happen for quantum Hall ferromagnets without a lot of very fine tuning. And I think this is an example of that. So I'm gonna show you an example that is sort of a puzzle. So I'm showing you here whole side data, and let me remind you that this bright yellow region here is the same region that has simple one-fold degenerate quantum oscillation. So it's the simplest region on the whole side. We think there's just a single Fermi surface and it's fully spin and valley polarized. And that's true throughout this whole region. But there's a feature in the middle of this region, which seems to distinguish, two sub-regions, and that feature sharpens and moves as a function of in-plane magnetic field. So it sort of suggests that there's, for example, a spin transition inside this region where the Fermi surface is remaining fully polarized within the isospin space. And so we can try to study that in a little more detail. So let's call these two phases. It's a little hard to see here, but there's in fact a boundary between them, phase one and phase two. Okay, and we can look at that detailed dependence along a cut like this as a function of the in-plane magnetic field. And you can see that there's indeed a cusp, and that cusp suggests that phase one must have a larger, you must have an in-plane magnetic moment at zero magnetic field, or in the zero magnetic field limit, and that must be larger than the moment of phase two, and that's why phase one is favored. Later looks like those moments maybe saturate to be the same thing. Of course, it could couple to some orbital degree of freedom, but we can exclude that by looking at the angle dependence in the plane of this magnetic field. So you'd expect if it's coming from some kind of orbital effect, you might see a threefold symmetry, or if there's some nematicity, you might see a twofold symmetry or something that breaks the lattice symmetries, but you don't. It looks completely independent of the direction of the in-plane magnetic field. And so that would seem to suggest that, okay, phase one is spin polarized and phase two is not spin polarized, and perhaps it actually has some antiferromagnetic texture, and that is canting at some low magnetic field until they have the same spin polarization, and that's why this phase boundary then stops moving afterwards. You can do a similar experiment with out-of-plane magnetic field, and you can find that actually it's the opposite effect. So as a function of out-of-plane magnetic field, you again have a cusp in the density at which this transition occurs, which means there's a cusp in the energy. And this time it's phase two that's favored. And if you actually look closely here, you can see that quantum oscillations cut right across this phase boundary. I can show you a zoom, and they don't, there's no change in degeneracy of the Fermi surface. So this is all physics of a single Fermi surface, but is coming from the underlying spin and valley textures. As it turns out, at least at our current level of thinking, there's no simple way to explain these two phases in terms of, one is spin polarized and valley polarized, the other one is valley coherent. It has to be actually something relatively complicated, for example, where the spin and valley textures are momentum dependent, and you have a Fermi surface that actually has textures on it where the spin and valley degrees of freedom are momentum dependent. And it is still a basic question we are trying to address as to what actually distinguishes these two phases, because they stay distinct, for example, even when they're both fully spin polarized. So that suggests that they have really different valley polarizations in some way. But this dependence sort of excludes the idea that one of them is simply uniformly inter-valley coherent. So it really does look like something rather rich. Okay, but maybe this is too many details. So let me turn then to some maybe zooming out again and tell you about the physics of Moire patterns. So what I've told you so far, right, is essentially that in ABC trilayer graphene with no Moire, the basic ground state at finite density, if you have a clean enough system, is a series of really quarter and then half metals and then full metals. There are some other complications, but basically the physics is itinerant ferromagnetism at low density. The only place where you see any gaps is at charge neutrality. Everything else is and sort of has to be a metal. There's really no lattice in the sense that you're only at integer lattice filling at zero density. So it's interesting. We certainly see interesting things at charge neutrality in ABC trilayer. I'm happy to talk about that. Although it's not dramatically different from what's been seen, for example, in suspended bilayers. But it's hard to play with gap states, and people who like topology, of which I am one, prefer gap states. Things are well quantized in gap states. There's lots of things that can happen there, and it's sort of easy to tell what's going on as compared to metals, where it's both theoretically less tractable and also experimentally a little harder to really understand. So a solution is, of course, to just add a lattice by patterning by aligning the ABC trilayer to a boron nitride, right? And this is a subject that was pioneered in Feng Wang's group at Berkeley, where they basically did this kind of from a different point of view, in the sense that they wanted to make a flat band. And so they went ahead and just made that, and it does indeed give you flat bands. I think one of the takeaways that I want you to take from the next couple of slides is the fact that that's not, I think, not quite the right way to think about it, because it's not the flat band that generates the interaction physics. I think the right way to think about this system in particular is that the interaction physics is there because ABC trilayer graphene is a strongly interacting low density semiconductor because of the intrinsic Van Hove singularities in the single particle band structure. And what the Moire does is it basically gives you a mechanism to generate gaps at finite density, and a variety of different gaps. And those gaps then have a variety of different, for example, Chern numbers and so on. So now you can get commensurate fillings basically at any integer multiple or fractional multiple of the superlattice filling. That will be some commensurate filling of a lattice, whereas again, without the Moire superlattice, you'd have to go at some extremely high density, far beyond where the interaction physics is happening in the unperturbed system. Okay, so let's just look and compare, right? So here is ABC trilayer with no Moire. That's the data that I've been showing you, right? So these variety of Stoner transitions, all these complicated phases. And here's ABC trilayer with a Moire, same type of measurement, same type of, range of measurements. And of course, they're both complicated, but the thing I want you to notice, first of all, is that certainly at low displacement fields, there's not a huge amount of difference, right? The physics is very similar, right? And at intermediate displacement fields, there's also not a lot of difference. You see the same, for example, on the electron side, you see the same Stoner transitions occurring, it more or less the same range of parameters. The difference is that at, for example, 4 holes per unit cell and 4 electrons, it's not shown just to match the parameters, you have some sort of energy gap in the Moire system, where of course you don't. That's just a high density metal at that point in the no Moire system. But then the biggest differences occur that you see these yellow streaks, right, which are high inverse compressibility. So that means a gap at 1 or 2 holes per unit cell start to occur at intermediate displacement fields. Okay, and the sort of remarkable thing is that you can compare these two phase diagrams, and you can see that the gap states in the Moire system, there's a very simple criterion that is almost perfect quantitatively for understanding the gapped phases of the Moire system, which are that whenever you have a commensurate filling of the Moire that overlaps in density and displacement field the region of parameter space where the non-Moire system was already magnetic, with a degeneracy of the Fermi surface that is, that matches that filling, you will get a gap. So in other words, we have a 1x state in our non-Moire system, let's say right here, right? We know that it is a singly degenerate Fermi surface. Well, when that singly degenerate Fermi surface occurs at a density corresponding to 1 electron or hole per unit cell, then you get a gap because it's at full band filling of its quarter metal state. Same thing goes for the twofold degenerate state. So you have a half metal, and as a result, you get a gap at 2 holes per Moire unit cell, and it's really very simple. Okay, and so I think that basically tells you that it is perfectly fair to start from in most cases you can start from the continuum band structure. Think about the physics of itinerant magnetism, and then think about the Moire as a small perturbation on top of that, which allows you to open up some small gaps. And those gaps will be gapped when the degeneracy is such that you're at full filling of a Moire unit cell in your reduced degeneracy space. Does the phase 1, phase 2 boundary intersect integer filling? Here, you mean? This is a phase 1, phase 2. I'll show you if your question is about the electron side, I will show you in a minute. If it's about the whole side, then there's not really a phase 1, phase 2 boundary. There's a phase 1 going into not simply connected phase 2 and a bunch of intermediate phases that we don't understand. Give me a couple minutes. I'm going to show that data in just a couple of slides, and then we can talk about it. We can, we can look at, for example, the topological nature of these gaps. So, these Moire bands in general, and indeed even the bands without the Moire pattern in general don't have a zero Chern number. Again, because of time reversal symmetry, you don't get anything on net, but we know we have time reversal symmetry breaking. All of those cusps in these various phase boundaries are telling you that there's finite magnetization. Of course, I showed you magnetic hysteresis also. So no reason not to have finite Chern numbers. Of course, this was also already observed by Feng Wang's group. So let's have a look, right? In capacitance, it's easiest to measure Chern numbers by looking at the trajectories of gaps as a function of magnetic flux and electron density, right? You'll get gaps with Hall conductivities and block band filling numbers that are either integers or occasionally fractions if you have some additional symmetry breaking or fractionalization. And then you can extract the Chern number just from the slope. That's this T quantum number for a given gap, and the block band filling from the intercept, which is really just the filling of the Moire lattice. So we can have a look, for example, up here at these Moire gaps and see that they're topologically trivial. They don't disperse with magnetic field. So this is at filling -1 and filling -2. And that's consistent with prior work. Interestingly, if you look at negative displacement field, you see that this nu equals -1 state is indeed a Chern insulator. There's a kind of cute thing you can see here, which is that at the single particle level, you expect just from single band physics, this was something that was pointed out by Feng Wang and collaborators, that you expect a Chern 3 gap. But what they found was a Chern 2 gap. We see the same, but it's very easy to see how this Chern 3 gap is the other leading state. And it's because of interband mixing that this Chern 2 gap becomes favorable, but they're really quite competitive until the lowest fields. And so you can kind of see this competition showing up. I think there's an interesting question here, which I'll get to in the second half of the talk, if I get to the second half of the talk, which is that we really see very little hysteresis. And this is similar to what was seen by Feng and David Goldhaber-Gordon and collaborators. It quantizes at a finite magnetic field, but it seems very weakly pinned. You don't see these like hundreds of millitesla magnetic hysteresis, which is typical, as I'll show you, of twisted systems. One of the questions that we have is really why. I think one of the answers that we have at this point is that actually these systems may be very clean, and there may be very little that actually pins the domain walls. And so one of the things we're thinking about is how to do that. I'll get back to that in a few minutes. But it's a question I want to leave you with, is that we know these systems are extremely clean in the bulk, and yet they're not. This is not a beautiful quantum anomalous Hall effect. It's not a quantum anomalous Hall effect at all. One barely sees any hysteresis here. One certainly doesn't see quantized hysteresis. That is an interesting fact of the fact that this system is now clearly much cleaner than, for example, in the other orbital churn insulators I'll show you. But let me show you a little bit. So this is, I think, a little bit in response to Ashvin's question. This is the same data, but now extended to a much larger range of displacement fields. And so now you can start to see some new things on the electron side, which were not, as far as I know, reported before. In particular, you can see that now when this one-fold quarter metal intersects with filling 1, you get an insulator. And when the half metal intersects with filling 2, you get an insulator. Interestingly, if I'm not sure if that so indeed this 1 to 2 intersects integer filling right here. This would be a place, Ashvin, where that would occur. It looks like it's about to do it if we could go to even higher displacement field. These are getting to be very large displacement fields. It's not so easy. There's also some sort of state at integer filling 3 here, which is kind of new. We're not really sure about it. There's also a bunch of states at fractional filling. So in particular, you can see gaps at filling 1, 2, and 3, but also 1/4, 1/3, 1/2, 2/3 filling of this band. And if you look at single particle band structure with a Moire, this is exactly, large negative displacement field in the convention that I'm using. Electron doping is right where the bands are flattest. Unfortunately, they're not topological. That's where their Chern numbers are 0, but they're well isolated from dispersive bands. They're also where they have the smallest bandwidth. And so in a sense, it's not too surprising that one starts to see incompressible states at integer filling. What is surprising to us, and we are trying to, puzzling over, is that although all of these states that we see at fractional filling seem to be topologically trivial in the sense that their Chern numbers are 0, they don't seem to be consistent with the simplest picture we would have had, where they would fully spin and valley polarize. And you would, so for example, even at nu equals 1, you have transitions at finite small magnetic fields from whatever the incompressible state is at 0 magnetic field into some incompressible state at some finite field. And that, to us, suggests that this is not the naive state, which would be simply spin and valley polarized, but rather some other state which has a smaller magnetic moment, a smaller orbital moment than the state that is spin and valley polarized, and a small out of plane field causes a transition. Similarly, there's other stuff that's going on that we don't understand. For example, there is a state at nu equals 2/3 at finite magnetic field, but very small. At half a Tesla, you get a bifurcation where you have a topologically trivial gap at 0 magnetic at 2/3 filling, but then you have a gap that has a Chern number of 1 that seems to be a Chern number, a Chern insulator within the lattice of this presumably, sort of Wigner crystal, pinned Wigner crystal, or commensurate charge density wave, whatever you want to call this state at 2/3, which is energetically competitive. It doesn't actually, it's not actually the ground state at 0 magnetic, but it's rather close to being a Chern insulator that spontaneously breaks the Moire lattice symmetry. These apparently are rather energetically competitive. We don't understand this at all, but it seems like a close. I think the positive. Sorry, before I turn to other systems, the positive upshot here is that I think we have a very clean system where we can explore both itinerant ferromagnetism, but also, and there seems to be plenty of puzzles there in terms of just understanding the interacting physics in that system. But then we can also put on a Moire and maintain that cleanliness. The thing we have not been able to do is to generate a band that is both topologically non-trivial and sufficiently flat to see lots of fractional filling states. That would seem to me like the most interesting thing to do, because that is presumably where something like a fractional Chern insulator would actually be energetically competitive. We haven't seen anything that has a fractional slope at any fields below, 10 Tesla in these types of Moire heterostructures. The fact that we have fractional occupation states that have non-trivial topology does seem to be a good sign. I really am very curious about what the right move is to maintain this type of quality and find a regime of parameter space where the bands are sufficiently flat but also topologically non-trivial, ideally with a Chern number of 1, so that maybe fractional Chern insulator states there are more obvious ground state. But okay, let me move on to sort of an alternative system with which I think probably more of you are familiar, so I won't belabor it. But twisted bilayer graphene, I think you all know about. You probably heard lots of talks about it already. This is a bit of a different Moire system in the sense that the Moire really change, because it's interlayer coupling, it's a much bigger perturbation to the single particle band structure of an individual layer than a boron nitride Moire is. And so you sort of, there's no sense of the Moire being kind of perturbative near the magic angle. It just completely remakes the band structure. I think the key features are that once you have this flat band, then you have the same sort of strong correlations that you have in what I just showed you before. The thing that I'm going to focus on is the physics of ferromagnetism, right, which was first reported here by David Goldhaber Gordon in Twisted Bilayer Graphene. You can see, contrast to the, say, precursors of quantum anomalous Hall effects in ABC, there's very strong hysteresis here, and over hundreds of millitesla and Barkhausen jumps that indicate sort of pinned domains, and so that's what I'm going to sort of tell you about for the. How much time do I have left so that I can pick intelligently what to talk about, because I doubt I'll finish.
Oh, gee, it would be good if you could wind up in 5 minutes or so.
Okay, fine. So let me just choose. Maybe 2 interesting things. So I'm going to skip sort of the older work, which basically says that when you make these systems cleaner, or really when you just make a few more of them, you can get lucky and find that in fact at, say, a filling factor 3 in twisted bilayer, you have a quantized anomalous Hall effect. So this is what that looks like as a function of density. Again, contrast with ABC, where there was no hysteresis. Here you have both very good quantization, but also these very discrete Barkhausen jumps. And what we have found and what we have been working on with magnetic imaging is that in fact, the types of Barkhausen jumps are directly correlated with structural disorder. So disorder in the Moire pattern itself. And I think that is probably a very important insight for how to design these quantum anomalous Hall systems in the future, because they clearly need some amount of pinning. And so how to engineer pinning, for example, in ABC trilayer, where you probably don't have any intrinsic disorder, at least not on this scale, seems to be important. I mean, the basic physics of this measurement to show you, right, is that we're measuring really the magnetic field with a small squid just above the sample, and you can do this at various points in a magnetic hysteresis loop and map out the evolution. Here it's plotted as a function of the local magnetic moment, which we extract by kind of standard Fourier techniques. And you can see that there are magnetic grains, really, which are absolutely reproducible in the sense that over many cooldowns, over many hysteresis loops, you can stabilize the exact same magnetic grain in this type of structure. And that basically tells you that it's directly correlated with some kind of disorder. And we have some evidence, which we're just developing, that this is not just disorder of the twist angle between the graphene and the boron nitride, but it's also disorder in the twist angle between the two graphene layers, but also between the graphene and the boron nitride, which you can extract by trying to map out the twist angle it's easy to map the twist angle, and where you see that it's not correlated with twist angle, sort of by elimination, it's correlated with other twist angles that are less obvious. Yeah, so maybe just to conclude, I'm gonna just tell you very briefly about this other system and maybe some, just for the sake of showing you some more unpublished data. This is work on another of these twisted systems. This is monolayer twisted on top of bilayer. The basic choice there is informed by wanting to have as little symmetry as possible, which seemed to be important for realizing these quantum anomalous Hall states. And in this system, we found that fillings 1 and 3 host quantum anomalous Hall states with Chern number 2. But the sort of interesting thing was that, in fact, the interplay of these orbital moments with charge carrier density was does an unusual, but I think very generic thing in these systems. So the physics I want to show you is that at nu equals 3, you have, as a function of magnetic field, a rather nice hysteresis loop. It looks like almost single domain, or certainly not very many Barkhausen jumps. But as a function of density, you see a very strange and switchy behavior, which at first I thought was just, there's a broken wire, something's wrong with the sample. And it turns out it's not. It turns out that there's a remarkable property of the fact that these are orbital magnets, which is that the total magnetic moment in these systems is very small. It's small because it just comes from the band electrons. There's not, a reservoir of localized spins in some d orbital somewhere that is providing the magnetization density. It's really just the block electrons that are occupied. And in a Chern insulator, there's a contribution not just from the wave packet self-rotation, but also from the edge states. And it turns out that that edge state contribution, which is related to the Chern number and the gap, can be bigger than the contribution from all of the filled states, to the point where it may reverse the sign. And this effect was predicted by Alan McDonald's group right around the time we were taking this data. And what I'm showing you here is the fact that when you have such a sign reversal in a topological insulator gap, in a quantum anomalous Hall gap, if there's a sign reversal as a function of chemical potential, which is essentially what this can give you, it means that when the edge states are empty versus when they're full, the total magnetization can be different. Well, then if you have metastable dynamics as a function of magnetic field, you're also going to have metastable dynamics as a function of density. And so what you can do is use your gate voltage to simply reverse the magnetization, introducing charge only at the edge. This is in a regime that's very close to a quantized regime. The lack of quantization is really from sort of small domains, small amounts of disorder. You're at Hall angles of 85 degrees or whatever, and so you can switch the magnetization completely using a gate voltage. So for example, just as a sort of cute example here is flipping the magnetic bit, which is this measured by this Hall effect. You can flip it up and down either by ramping the gate voltage or by ramping the magnetic field. They have the same effect, and you can do this totally reproducibly and over again. So yeah, perhaps the final thing I'll show you in just a minute is that in this system too, we're starting to get a little bit ever closer to something topological at zero magnetic field. So in particular, we found that in addition to these Chern insulators with C equals 2 at half integer filling, so that means 3.5 electrons or 7.5 electrons per unit cell, you also get gap states in this system. Only this time they actually have some finite Chern. Sorry, that should read C equals 1. And so this is, their transport is hysteretic. There's clearly broken time reversal symmetry. Things are not perfectly quantized at zero field, but they certainly have large Hall effects. And it looks like what's happening is you're going to half filling of a Chern 2 band and breaking the lattice symmetry, but partitioning the Berry curvature above and below your gap. And this makes something called a symmetry broken Chern insulator, which is basically a Chern insulator with a doubled unit cell in this case. This is the first time we've done it at zero magnetic field that we've seen. I think, again, it's sort of telling you that interactions are strong enough under certain conditions that you can go beyond sort of just rigid filling of different spin and valley flavors, a little bit beyond the most naive exchange physics. Again, very curious. How does one make a fractional Chern insulator? That would be a real feat, something that we're very interested in. Would love to hear opinions from the many theorists here who I know are engaged with this problem. So, so let me just conclude here and acknowledge in particular Haushin, my graduate student who led the work on ABC trilayer with the help of an extremely talented undergraduate, Kian Shea, and Charlie Cheerhart, Gregory Polshin, and Marek Serlin, who led the work on both the magnetic imaging and twisted monobilayer. So thanks everybody for your attention. Sorry for going over.
Well, thank you so much. It really hot stuff. I mean, it's a lot of nice things happening. To ask questions, we have time for a few questions. Please type them into the chat, and then I'll read them. To get started, maybe I could ask you sort of a. It seems like the cones associated with the Dirac points are acting like spins and sort of replacing the regular spins for magnetism. And do you have a few more words? You were talking about textures, spin valley textures, and all of that, about the right way to visualize that for us?
I mean, yeah, I think there's a sort of naive way that you can say that in a given valley, you have, the magnetic moment that you're playing with is a little orbit in the 2D plane. And it's small, but it's, I mean, the Moire case at interference, like the size of the Moire unit cell. But that's obviously anisotropic. I mean, an electron can orbit in the plane. It cannot orbit, perpendicular to the plane. Right. So that gives you an intrinsic anisotropy. That's an easy axis, a very strong easy axis. And so I think you can just think about it as, there's some microscopic easy axis moment that is around, and that is a suitable degree of freedom to order, and it'll generate a finite magnetic moment, and thermodynamically it's going to be the same. Should I just answer some of these questions in the chat?
Go ahead.
Yeah. So Yang Long asked, do you expect to see Pomeranchuk effect in ABC trilayer with and without Moire, since in both cases you see many isospin transitions? Excellent question. We've been looking rather closely at that. So far, there's a lot of temperature dependence to those transitions. So far, everything looks like normal transitions, and that there's no we don't see anything favor. We never see the temperature favor the more ordered state. It always favors the more disordered state. But it's something we're looking carefully at. But it's a good question. Yeah, and because these are really first order transitions, unlike in twisted bilayer graphene where I think they're not. In principle, it should be very obvious. And in principle, you should actually be able to make a sort of electronic refrigerator if you found a Pomeranchuk effect with a real first order transition. But so far, no luck. So Mary Kreidel asks, you mentioned that the domain walls are not well pinned. You know how the domain walls are affected by strain, particularly near the edges of the sample. What we know is that the domain walls are always pinned to the same places in the sample. That's what we know in twisted bilayer graphene. And what we know is that in ABC trilayer graphene, they don't seem pinned at all, as far as we can tell, or very, very weakly. And so we don't know. I think trying to think about, making constrictions or, utilizing surface tension and what the right design is to try to pin them by geometry and edges is an interesting thing. And as far as how they're affected by strain, I don't know. Yeah, I don't know. Presumably they are affected, but I don't know. And let me answer Philip's questions. The magnetization shown in the squid data quantized per Moire unit cell. Yes, it is. So it's about, our peak magnetization that we found is something like 4 Bohr magnetons per Moire unit cell. With an error bar of maybe half or 1 Bohr magneton. So quite a bit more than 1 spin per unit cell. And Ashvin asked in the chat, do you see any sign of rotation symmetry breaking in the new 7/2 sigma XY state? We have not looked at that in the way that we would like to with an in-plane magnetic field, but I think it obviously has to break rotation symmetry breaking because it's a unit cell doubling state, right? I think. But we haven't seen an explicit thing. The problem is that if you look at these twisted heterostructures, which have a lot of Moire disorder or really any Moire disorder, it's very hard to not see anisotropy with in-plane magnetic field. And it's a little bit hard in transport, especially it's a little bit hard to know what to make of that. So yes, we want to look at that, but we don't have the data that I think you're asking about, but it's on the list of things to do.
Okay, well, that's great. I guess one last chance for additional questions. 10, 9, 8. Okay, I guess that's it. It's a really exciting talk. Thank you so much for visiting us.
Sure, thanks. Yeah, if anybody wants to chat a little bit less impersonally, just drop me a line or let me know. Yeah, bye.
Great. Thanks so much.
Thank you.
Thank you.